Hi everybody, we're going to go over a 7.5 problem for the homework. 7.5 is where you compare means from samples that are matched. We call them matched pair samples. You have the same measurement being taken under two different conditions in samples that have a one-to-one pairing between them. And usually that means that it's the same individuals just being measured under two different conditions. And that's what you'll see in the problem we're about to look at here. We're going to compute the change in the mean, basically, between the two conditions. So let me start this up. We're going to do question number 3. And so let's look at this. It says a study was completed to investigate whether oat bran lowers serum cholesterol levels in people. A random sample of 13 individuals were randomly assigned a diet that included either oat bran or cornflakes for breakfast, I guess. After 2 weeks on the initial diet, serum low-density lipoprotein levels were measured. Each subject was then crossed over to the alternate diet. After 2 weeks on the second diet, the LDL levels were once again recorded. The data are recorded below. Assuming the population of differences is normal, we're going to test the claim that the mean lipoprotein level is higher when patients are eating cornflakes for breakfast than when they're eating oatmeal. So basically, make a couple of notes here. The first thing that it makes clear is that our alpha is going to be 0.04. Okay. We're going to have two means. We're going to have mu1. This is going to be for cornflakes. Okay. And we're going to have a mu2. And that one's for the oat bran. Okay, and these are average LDL levels. Okay. And the alternative hypothesis says that the LDLs are higher on average when people are eating cornflakes. So that is to say that mu1 is bigger than mu2. I'll just hold back any Pokemon jokes. The null hypothesis is that mu1 is equal to mu2. So there's no difference between the LDL levels on average. Okay. Just a quick reminder, mu d is mu1 minus mu2. Okay, and so if mu1 is equal to mu2 here, that tells us mu d is 0. The mean difference is the difference of the two means. The mean change in cholesterol is 0, and so that is to say it doesn't really matter what kind of cereal you're eating, you're going to have the same LDL levels for cholesterol on average. Okay, and so we got all that. I guess I can go ahead and put in my null hypothesis. On this one, you're going to have to go into the variables menu. So if you click on that, there's a mu1 and then type equals mu2 there. Okay, and then for the alternative hypothesis, we're saying mu1 is greater than mu2. So back to variables, mu1 greater than mu2. It's so hard not to tell the Pokemon joke. I'm trying really hard. Okay, I've already said it. You know, how many times am I going to use the same stupid joke? Okay, so here we go. Okay, it looks like a right tail test to me. And so then what you need to do is compute all these differences. So the 4.24, we're trying to see how much the LDL's changed on average for people. So for the 4.24, you're going to subtract the 4.66. Like that. So that's going to come in as a negative 0.42. Okay, so then the next one, we're going to do 3.51. minus 2.90. So here we get positive 0.61. And I'm not going to type all these in. I've already done these in advance. So let me just look at this. I've got the rest of them. I took a picture of them. So I'm just going to put these in. So the next one should be 0.67. Then negative 0.27. Okay, then 0.43. Then 0.10 if you like. 0.06. 0.30 or just 0.3. Okay, so then after that 0.16, then negative 0.19, 0.20, okay, 0.46, and finally 0.31 should be the last one. And then obviously at some point we're going to need to check these. Actually, I'm just going to do that right now, see if they're right. Everything's good. Okay, so that's important. And then is it a right tail, left tail, or two tail test? We say mu1 greater than mu2, so that makes this a right tail test. All good. And then the criteria for normality. The criteria are with averages typically are that your sample sizes need to be bigger than 30 or your population needs to be normal. Okay, now in this paired samples problem, the sample size is the number of pairs. So it's actually the number of individuals, not the number of values that we got. So there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think 13 values, which of course is not bigger than 30. So that's a problem, but not too big a problem because back here it says assuming that these changes in LDL levels, the differences, are normal. So we get to assume they're normal, and therefore we'll say the criteria are satisfied because our population is normal. So I'll go ahead and select that. Okay, we're good to go. Now, for the D-bar value, just to kind of let you know, I have already keyed all the differences into the calculator here. So here are the differences, just pre-entered basically. And so then I'm going to go ahead and clear out of there and then just go ahead and do the computations. So it's one variable stats. We're just doing the differences. Okay, and here are our statistics. So I'll go ahead and write some of this down. Okay, so our N is 13. The X bar is actually D bar. That's the mean of the D's. So we'll change X bar to D bar. It's equal to 0.186. And then SD, the standard deviation of the D's. The calculator is calling it SX because the variable is X on the calculator. So it's 0.331. Okay, and we can go ahead and put all that in here. Okay, and I'll go ahead and check those, make sure, yeah, so we're good here. And then we'll have to do this test statistic. So here it comes. It's a t-test because we're using a sample standard deviation. Oops. So d bar minus mu sub d over SD divided by square root of n. All right, so the D bar was 0.186. Okay, up above here we're assuming mu D is 0, so this will be minus 0, and we'll always have a minus 0 there. So you don't really need to put it in on the calculator. I will, just because somehow it just looks better to me. And then the SD has the 0.331 over the square root of n. That'll be the square root of 13. Like that. Okay, so let's clear this and do the computation. Oops. Again, I don't need to type -0, but I'm just doing it for the looks of it right now. And 0.331 over square root of n, which is 13. Okay, so that's actually more than 2 standard deviations different from 0. So that may be significant. 2.026, or may not, I don't know. Depends on the level of significance when it's this close. Okay, so we'll see how that goes. All right, so we'll put that in here. 2.026, they want 3 places. Okay, check it. Okay, so that looks good. All right, now our level of significance, I think I wrote down up above here. So alpha was 0.04. The T critical value have not looked up. So this is a one-tail test here. And I guess I'll make that note. I didn't before. So right here, we know this is a right tail test. Okay. And so I can do a little bell curve maybe down here. And pardon me for being a little neurotic about that. I screwed up. Hang on. Okay, that's better. So on a right tail test, my my critical value will be on the right. So this will be my T critical value. The tail will have an area that's equal to alpha. And alpha is 0.04. Okay, so critical values will all come from table A2. So again, we're doing 0.04 one tail. Now the degrees of freedom are n-1, so there's going to be 12 degrees of freedom here. So let's go ahead and jump down to the table. Okay. So again, one tail, alpha is 0.04, so that's this column. Okay. The sample size is 13, so n-1 is 12. That's our degrees of freedom. And then this gives us our requirement for statistical significance. 1.912 is the number of standard errors required for statistical significance. 1.912. I'll go ahead and clean this up. And just to note what we've got here, the T critical value will be 1.912. Okay, and then we'll note that our test statistic here is bigger than that. It is in the tail. I'll just put a dot somewhere to the right of 1.912. And being in the tail is enough to call it significant. So we are going to have significant evidence for our for the alternative hypothesis. That's just going to mean that the LDL levels were higher for the first group and it was significant. Okay, let's go ahead and answer some of these questions. Okay, so critical value is 1.912. It's going to want a p-value next. We did say yes, the t test statistic indicates the mean is significantly greater. The mean for the first group, cornflake group, is significantly different than the oat bran group, which means the mean difference is greater than 0, which is what we have here. So we'll go ahead and check all that. Okay, so then the p-value, let's go with that. Now I'll just get another picture of the distribution. Okay, so here we go. I'll go ahead and put my test statistic down now this time. So this is the 2.026. Okay, that's the T test statistic. Okay, that tail there in the right is a right tail test, so the tail in the right will be our p-value. Okay, we'll go ahead and diagram the table here. It's table A3. Okay, so for degrees of freedom, as usual, we go with n-1. That'll be 12. Okay, our test statistic here, we're just going to have to do 2.0. So it is the 2.026, but we have to round this to one place after the decimal because that is all the table will tolerate. So from 12 degrees of freedom and a 2.0 test statistic, let's see what we get here. Coming pretty close on this one. So 12 degrees of freedom right here, and 2.0 for the test statistic. Yeah, 0.9657. And then just a quick pointer here. This is the area to the left of our test statistic. This is a right tail test, so we want the area to the right. Okay, so anyways, 0.9657, I'll clean that up. Wrong way. Where is it? Oh God. Oh, here we go. All right, so it said 0.9657. That is not the p-value, it's the area to the left. So for our p-value, we're going to have to do 1 minus that. So I'm going to try and write this down real small. 1 minus 0.9657. So do that on the calculator real quick here. Okay, so 0.0343, that's our p-value. It's pretty small. And in fact, it's less than 0.04, which was our alpha. So we will be rejecting the null hypothesis. Go ahead and put this in over here. 0.0343. Hopefully that's good. And then this thing, obviously it is good here. We'll go ahead and try and dial in the p-value. I just once again, I'll emphasize that the software here is not really precise that I was using to make these. So the software is trying to compute the p-value, but it's not the best. It's just not the most precise software. So, and there's nothing I can do about that. So the test statistic, though, we want to put in, what does it say, to the nearest tenth, I guess. So the test statistic was the test statistic was 2.026. So we'll dial that in here. Just put it in as a 2.0 like that. And you can see the p-value. So, oh, I did the wrong number here. So 2.0, and the p-value here at 0.034. What did we get? 0.343. So that's actually pretty darn good. We'll go ahead and check that. It'll be fine. Come on. Okay, so everything's good here. And then the decision part is just again reminding you that you reject the null hypothesis when the p-value is less than alpha. So our p-val, we want to focus on the point 0.03, and then I'm going to obscure the 4.3. Just focus on 2 digits. 0.03 is less than 0.04, which is our alpha. Okay, and 3% and 4%. 3% is less. Okay, and then less means reject. Greater than or equal means fail to reject. But this one's less. So that means we reject the null hypothesis. And we'll support H1. And then just to note, H1 had said, coming up here, it says mu1 is greater than mu2. So that is to say, let me put it down here, mu1 greater than mu2. That the mean lipoprotein level, I guess, lipolipid, I don't know, the LDL level, okay, for cornflakes, the mean is greater than it was for oat bran. So that's a kind of like a big wahoo for cornflakes. I believe the data here came from some source. It did cite a study, but I used the study and then I randomized the data, so it's not exactly the same data as with the study. So you know, it's sort of close, and you could Google this study and I think you'd find it. Anyway, going back down here, I think we can say that we're going to reject the null hypothesis and support the alternative. And again, the alternative says that the mean lipoprotein level, the mean LDL, that's the safest way to go. The mean LDL was higher for people on cornflakes than for oat bran. So the data support the claim here that the mean lipoprotein levels are higher when eating cornflakes for breakfast compared to oat bran. And so we should be good to go. 7 out of 7. All right, so that's basically how a right tail test would work. A left tail test would say mu1 is, just kind of going back up here, left tail test would say mu1 is less than mu2, and then the two tail test would say mu1 is not equal to mu2, and you just got to kind of figure that out as you read the problem. Best of luck, everybody, with 7.5.